Давайте подождем еще пару минут. So let's begin. Hello, everyone. I will share my screen now. Do you see the screen and hear me?
Yes.
Okay. So first of all, I would like to finish the part with Fabry-Perot resonator and S matrices from the past lecture. So let me write S matrix that we obtained for Fabry-Perot resonator. One. Is it correct? I think yes. This is what we obtained for the Fabry-Perot resonator. So also we need expression for B2. Also A1. So these are our results from the past lecture. So what we can do now? We can calculate the transmitted power. So in this case, we want to calculate such quantity A1 squared. So is nothing else than t1 squared, t2 squared, and the modulus of the denominator r2 phi squared. Yes, something like this. Let now, for simplicity, consider such case when r1 equal to r2 and equal to r. What we obtain. Also, we remember that t is 1 minus r. So here we obtain 1 minus r squared. And here we will open the bracket. So 1 minus r in power 4 and minus 2 r squared cosine 2 phi. And also we will subtract r squared to minus 2r squared and add 2r squared. And we see that we can combine this part. Next, what we have here, also 1 minus r squared plus 2r squared 1 minus cosine 2 phi. We also can simplify it further. Just divide by 2 and multiply by 2. And in the end, we obtain 1 minus r squared 1 minus r squared plus 4r squared sine squared phi. Yes, this is expression for our transmitted power. So we can analyze it. For example, we can plot it. Let's plot phi. What we see here. Where is the maximum? What is the maximum value? Obviously, it is 1 when sine equal to 0. So in this case, all power transmitted, and the maximum value is 1. Then the minimum value also obviously when sine equal to 1. So in such case, we can plot such dependence to pi. We have some kind of resonances here. Well, also we can find the distances between these maximums. Oh, how? We can consider our phi. As you remember, phi is kz d. Let's rewrite it. Omega over c cosine of incident angle multiplied by d. And we consider maximums, where maximums located at pi m. M is just integer number. We can also, it is more convenient to consider it in frequency domain. So we can write pi cm d cosine theta. Or usually people also consider not the angular frequency, but just frequency that divided by 2 pm or 2 pi, sorry. So f m mode equal to mc 2d cosine theta. And how to find the distances between two peaks? Well, we'll just need to write such expression. Obviously, it equal to 2d cosine theta. This is expression for distance between two peaks. Also, it is important to consider the full width at half maxima. So we know that at half maxima we have 1/2. I will call it full width half 1/2, and our expression, I will just rewrite it. Minus squared divided squared sine. So let's simplify it. 1 minus r squared plus 4r squared sine phi squared equal to 2 1 minus r squared. This we can find sine squared phi and 1 minus r squared. Here we say that, for example, r is close to 1, and in this case also phi is small, so we can neglect the sign and just consider phi and obtain phi x plus minus r squared divided by 2r. Or we want to find the width, so delta phi equal to 1 minus r squared divided by r. Or again, it is more convenient to consider it in frequency domain. So we can obtain that in frequency domain it equal to sine. So it's expression for full width at half maxima in frequency domain. Another important feature of such systems is contrast or resolution. We consider So you divide the position on full width of half maxima. Obtain r divided by 1 minus r squared. This contrast. Maybe I'm wrong, but in some literature it called finesse. Now let's consider another, maybe last for today, for parameter of our system is quality factor, Q factor. I think most of you already know something about the Q factors, but now let's consider the Q factor of Fabry-Perot resonator. So in order to find the Q factor, we must look on our scattering matrix. So you remember that we have some denominator in front of matrix. 1, 2, 2. This is our denominator. Obviously, see that it has some poles in it. Let's find them. So again, we say that R1, R2 equals just R for simplicity, and also consider R is close to 1, or we can write that R equal to 1 minus some small parameter delta. So let's find the poles. We must look at the denominator. So 1 minus r squared e to I phi equal to 0. So in order to find poles, we must consider such equation. So let's substitute. 1 minus delta squared e I. So again we say here also phi small. Let's expand it. 1 minus 2 delta, and delta squared we just neglect as small parameter. 1 plus 2 I phi. So next, 1 minus 2 delta plus 2 I phi. We also neglect the term delta multiplied by phi because it's small, equal to 0. And here we also obtain that phi equal to delta, or phi equal to minus I delta. So we now obtained the imaginary part to our pole, but we also know from here that poles actually this equation, this denominator have a lot of poles. This exponent give us a lot of poles. Obviously, it is close to pi n, just n, not to be confused with m, also integer number. So the final expression for phi, we obtain that equal to pi n minus I delta. So we have the real part and imaginary part. Oh, yeah. Doesn't matter. So as you remember from the math courses, where these poles are located? Obviously, it's located somewhere below this line. So basically, it means when we have a scattering of the wave on our structure, we obtain some resonances. Or in other words, we also can say that we have our field, incident field A1, it is outside. And then because of our denominator of S matrix, the field inside becomes bigger than outside. Well, as you remember, we calculated A tilde and B tilde. So in this case, the field inside of our resonator is bigger than outside. And this minus I delta that we obtained here is nothing else as decay rate. So maybe you remember the oscillator, maybe you solved some problems, even in bachelor, you obtained something like minus I omega t minus I gamma t. So it is, this gamma is just the same as the decay rate. So for frequency, for M's frequency, we easily can write that equal to cosine theta here by M, and also I will write it like this, minus I delta here. And now we easily can write the expression for the quality factor. 1 over 2 pi, pi M, and 2 delta. So you remember the real part of the frequency divided by 2 imaginary parts. Or we also can rewrite it of M plus 1 minus M divided by delta phi multiplied by M. Well, this quantity basically show you how fast the field will decay. So you have some excitation, you turn it off, and fields start to decay. And this quantity show you how fast it will decay. Also important feature here, you see that here we have M. So it means that the more number M we have, the more quality factor we obtain. But why? Can someone answer why? So M is just a number of mode, number of frequency. So okay, basically, when you increase M, your frequency increases and wavelength decreases, obviously. And when we have lower wavelengths, we will have more lambda over 2 in our structure, in our resonator. So in this case, we have more half wavelengths in our length of resonator. That's why the quality factor grows. Okay. So
sorry, can you
yes.
please repeat why if we have more half of wavelengths in resonator, we have more quality factor?
So basically, maybe you remember from other courses the resonance condition of some Fabry-Pérot resonators. So it's just we have D is the length of resonator, lambda over 2 multiplied by some integer number. So it is just the resonant condition of Fabry-Pérot resonator. So when you're here, when you increase M, you increase the frequency. So because it's here. When you increase frequency, the wavelength decreases. So, but the length of the resonator is fixed. So now more half wavelengths fit in our resonator. That's why we have more. You remember that we considered such scenarios. So in this case, we will have more reflections from mirrors. So that's why we will have more Q factors. Did I answer your question? Is it okay?
Okay, thank you.
Okay. So now I finish with Fabry-Pérot resonators. If you have some more questions, please ask, or I will continue with new topic. So okay, if no more questions, let's start. I guess the last topic in our course. So coupled mode theory. We just today we'll just know the basics of coupled mode theory. Well, actually, it is quite common theory in fiber optics when you have a waveguide and you have different modes in waveguides, and due to some difference in permittivity or something else, we have some perturbations. So let's consider some waveguide, just arbitrary waveguide, and say that we have two different modes in this waveguide. This leads to we also can have some perturbation in permittivity, and these two modes can overlap and lead to some hopping between modes. Modes can overlap, and it will just interfere somehow. And today we'll see how it happens. So the starting point of this theory is reciprocity theorem that we obtained with S matrices, but we will now obtain it in different form. So for example, let's start. We have two different solutions. Let's say the first one. I will write it. I omega mu over C and magnetic field I over C G 1 minus I omega 1 divided by C E. It's the first mode and the second mode. I will write it in such manner. So E2 conjugated. Omega divided by C. It also H2 conjugated. Magnetic field I over C G2 plus omega 1 2 R over C E1. So it's the second mode. Let's now multiply this one. This H2 conjugated conjugated. This one H1, this one E1. So we did it several times already. Let's do it. First, let's consider this equation. Sorry, no, not this one. This one and this one. Also. And let's subtract them. For the first one, we obtain H2 conjugated curl E1 minus E1 curl conjugated. This is nothing else. Divergence. The right hand side, I omega mu1 R C H1 H2 conjugated minus I omega epsilon 2 R divided by C conjugated 1 and the term is J2. I also forgot this. And also conjugated. And the second pair of equation I will just write the divergence of E2 H1. The right hand side minus I omega C to I'm sorry, guys. In second pair, mu and epsilons also should be conjugated, because in general case it can be a tensor. So strictly speaking, it must be conjugated. So here conjugated. Here also I forgot conjugation. Conjugated plus omega epsilon 1 r over c 1 conjugated minus c conjugated v1. And what we can do with it, we can just sum them up. So I will write sum up. Obtain a large expression. So the divergence conjugated plus conjugated 1. This is the left hand side and the right hand side. So we can combine some parts. So epsilon 1 r minus epsilon 2 conjugated r multiplied by E1 conjugated I omega over C. The same thing with mu. Magnetic field. And the currents. 4 pi C. K1. Plus K1. So this is our reciprocity theorem in conjugated form. So it's the starting point of the coupled mode theory. So now let's consider some waveguide. I will try to draw it, some waveguide. We have some waveguide. Actually, it could be arbitrary shape. So we have some waveguide and consider such volume. such volume, and it is perpendicular to Z. So this is our V volume. Volume is perpendicular to Z axis. Also, let's call this divergence like just some f. And we want to calculate the such integral dv divergence of f. How can we do it? So we can consider first of all, we can write it like the SF as S. We can split it in several parts. For example, let this part be S1. S2 let be the opposite part of this volume. And we also have this part. We need to integrate over. Let's call it S3. We need here also the normal vector. So now we can split this integral in 3 parts. So first of all, we can write ds over S1 f, but we also should write the normal vector z, and in this case there should be minus the second part plus over S2. We have almost the same integral z, and the third part is 3. Analysis ds normal vector and f. So in the end, we will just expand this volume to the infinity and get rid of some contributions. We also say here that in waveguide, our function f doesn't have any singularities. So for now, let's consider the first and second integral. I will write it. Consider S1 and S2. I will write it as one integral over some s ds minus f z xyz plus f z y z plus some delta z. So this delta z. And also I will write S3 ds and f. So here it is obvious that if we have some waveguide solution, our fields are localized inside this waveguide and decreases exponentially outside. So therefore, well, in the end, we will say that it will be 0 because f, our function f, outside at the infinity will be 0. So let's rewrite some parts. F z x y z plus delta z. What is that? We can rewrite it as f x y z plus some small parameter. Say delta z y z. It's quite obvious. So continue our equation. So delta z d over dz integral ds fz x y z and also some delta z and the contour integral dl. This is L. It's just our contour. And F. And it can be written as delta z integral ts divergence. So it is possible only when only if our f doesn't have singularities inside the waveguide. So delta z we can yes, it neglects now. So we write divergence f to d over dz integral ds z x y z. And I will not write the this part because it goes to 0 at the infinity and we can neglect it. So this is our final answer for now. Perfect. Now we can do something. Now we want to expand these solutions in terms of waveguide modes or eigenmodes of the waveguides. It is actually it is called eigenmode expansion. So imagine we have waveguide solutions. So waveguide solutions. So we have the same waveguide, for example. That we have two different eigenvalues or modes. For example, first one alpha is E alpha x y E, I, K, alpha, Z, and beta. E, beta, X, Y, E, I, K, beta. So this has two eigenmodes of the waveguides. So now let's also do some simplifications. We say we have no current, also mu1, mu2, epsilon1, epsilon2, and also epsilon1 equal to epsilon1 conjugated. Actually, I will just say it without one. It means we have no losses in our waveguide, just for simplicity to show how it works. And let's substitute these solutions into our reciprocity theorem. So as you remember, here it's freezing for some reason. So because permittivities are equal and we have no currents, the right hand side of the reciprocity theorem will be 0. So we now consider only the left hand side. So let's substitute it. Also from here, the divergence. Let's say that integral ds and substitute our part E alpha H beta conjugated over Z, because here we have only Z. E I K alpha minus K beta Z plus beta conjugated alpha. Here also I K alpha minus K beta Z equal to 0. So we can calculate the derivative, and finally here we obtain K alpha minus K beta via S H beta conjugated plus beta conjugated H alpha. Also equal to 0. So we see that this is because we have two different modes. It is definitely not equal to 0. And so this part is our orthogonality. Orthogonality relation of the modes. But also they should be somehow normalized, not only or be orthogonal, also should be normalized. And we say, what if if alpha equal beta, what we will obtain? Let's just substitute ds alpha conjugated plus conjugated alpha. What we obtain? This is nothing else as two real parts of such relation. E alpha, H alpha. And if we will rewrite it a little bit as 2 4 pi over c multiplied to c or 8 pi, sorry, pi. And here the real part ds E alpha H alpha. So this is nothing else as Poynting vector. And finally, we obtain the normalization of our modes. 16 pi over c, and I will call it p0. This is normalization. So it means that we can write it as E alpha H beta conjugated times and say 16 pi over c p0 and delta alpha beta. So now we can consider some cases and build some perturbations. Maybe let's make a 10 minutes break, guys, and we will continue and in 11:10. So let's continue, I think. So what we obtained? We obtained the reciprocity theorem. Then we made eigenmode expansion. We found that we found orthogonality condition, and also found the normalization of these modes. Now we can consider some examples. Let's consider some waveguide with permittivity perturbation. We can say that permittivity behave like y plus some delta x y z, some perturbation. We should substitute our solutions into the reciprocity theorem. So let the first solution be so, for example, we have some two solutions, E1 and E2. Let the first one will be with perturbation epsilon xy plus delta epsilon, and the second one is unperturbed, just epsilon xy. What we can write? We can write divergence of E1 H2 conjugated plus conjugated H1. And since we have different permittivities, we now have right-hand side. Epsilon, I say epsilon 1 minus epsilon 2. Here also E1 conjugated. So this is nothing else as our delta epsilon. We know that this correction is small, and let's find solution in the following form. So E1 is just the sum of some modes, amplitude, some E alpha x, y, I, z, and also H2, oh, H1, sorry. Alpha, y, I, alpha z. For second mode, the same. And let's substitute it first to the left-hand side, and integrate over small delta z. And also let's change indices to our alpha and beta. What we will obtain d or dz. This is our results from previous calculations. So now we have beta A beta z Mhm. Alpha H beta conjugated. E alpha minus k beta z plus beta conjugated times h alpha. And again, the same exponent. Z. Mhm. What to can rewrite it? Sum of beta a beta z alpha minus k beta z and multiplied by our integral that we obtained already. Delta alpha beta. Or we can also simplify it further. In the end, obtain d over dz beta z and 1 over c is 0. This is the left-hand side. The right-hand side. Yes, let's substitute it. I will write it I omega over c in front of the integral ds, some our delta epsilon, and here some alpha a alpha z, also a alpha e beta conjugated. And almost forgot I alpha minus k beta z. There's nothing else. E alpha minus k beta. I also forgot the omega over c. Delta epsilon y z and our fields. This is the right hand side, and finally, what we can write d over dz a beta I alpha z I alpha minus k beta z on some coefficient kappa beta alpha, where kappa beta alpha of 16 pi E0 and integral d epsilon y z alpha e beta. Mhm. Yes, and this coefficient is called Hoping coefficient. So basically, if you don't have any perturbation in permittivity, you will just have one mode, and that's all. Yes, maybe now we will consider another example. Maybe it will be more obvious. Let's consider for now two waveguides. First of all, we pump one of them and want to see how energy propagate in this situation. So how the modes are overlap, how the modes are propagate in such systems. So just two waveguides close to each other. We pump only one of them and see what happens. From obtained results, we can build such system. So dA over dz. So the first mode I kappa alpha alpha A plus I kappa alpha beta B multiplied by exponent K minus K. Yes. This is for the first mode. For the second one, we'll call it B. Almost the same. Beta. Sorry. This is again alpha. Let me rewrite it. Alpha and beta B plus beta alpha A beta minus K alpha. So this is our system for such situation. You see, this Hoping coefficients say that if they are non-zero, one mode will generate another mode, and vice versa. So let's solve it. And first, we must say that we want to neglect diagonal components of our matrix. So what we can say? Let's say that a z equal to some a tilde z and I alpha alpha z. And the same with b. Tilde z beta z. And let's substitute in our system. So we obtain t a tilde over dz I kappa alpha beta b and big exponent beta minus alpha alpha plus kappa beta beta. Also for b tilde or dz I kappa beta alpha a, and here we have k beta minus k alpha plus kappa alpha alpha and minus kappa beta beta. For simplicity, let's call this part is just kappa. So this one will become kappa conjugated. This we call 2 phi, and obviously this is also conjugated, so it's 2 minus I phi. Let's rewrite it. di tilde of dz kappa beta tilde into I phi z beta tilde kappa conjugated a tilde minus 2 I phi z. So let's find the solutions of such system in the following form. A lambda 1 z and b capital B I lambda 2 z. So obviously we'll have some exponential solutions. That's why we just consider it like this and substitute into the system to obtain I lambda 1 again. I lambda 1 a kappa b e I phi plus lambda 2 minus lambda 1. Good. And the second one, lambda 2 b I kappa conjugated a minus minus I to 5 minus lambda 1. And we also see that to have a solution, we also should write, well, first of all, I will neglect imaginary units, and we also should write that 2 phi plus lambda 2 minus lambda 1 to 0. So from this equation, we want to find lambda 2. And let's substitute it all. Lambda 1 A equal to kappa B. And the second one, conjugated A equal to lambda 1 minus 2 phi B. So for the first waveguide, what we can obtain? We obtain that lambda 1 over kappa conjugated as kappa over lambda minus 2 phi, or lambda squared minus 2 phi lambda 1 equal to kappa square modulus. And let's solve this equation. Minus 2 phi 1, and here we add phi squared, and here also we add phi squared plus kappa squared, and we easily obtain that lambda 1 plus minus phi plus minus square root of phi squared plus square modulus of kappa squared. This means basically that our solution A z is nothing else than some A1 constant I lambda 1 plus z constant A2 I lambda 1 minus z. We also want to make this square root as some gamma for simplicity. So for the second waveguide, what we have, we can just say that B is nothing else that kappa conjugated A divided by lambda 1 minus 2 phi. And easily we can write the solution. Just substitute lambda 1 minus 2 phi and obtain kappa conjugated 1 lambda 1 plus minus 2 phi the 1 plus minus 2 phi z and the second solution 1 minus 2 phi and the exponent minus 2 phi z. Mhm. And finally, let's write the final expression already with gammas. 1 I gamma z plus a2 minus I gamma z и I phi z. And the same story for B. So I have here kappa conjugated minus a1 phi minus gamma I gamma z minus 2 phi plus gamma gamma z minus I. Perfect. We found the solutions. So let's now consider the simplest case when at z equal to 0, all energy is in the first waveguide. Or in other words, we can say that A tilde of 0 equal to 1 and B tilde of 0 equal to 0. All energy in the first waveguide. So first we can say that A1 plus A2 are 1. So A2 equal to 1 minus 1. And from second equation, we can say that A1 divided by phi minus gamma plus A2 divided by gamma equal to 0. Let's try to solve this system. So phi minus phi plus gamma A1 plus phi minus gamma 1 minus A1 equal to 0. A1 minus plus gamma equal to minus phi minus gamma. So in this case, we'll say that A1 minus phi minus gamma divided by 2 gamma and A2 is just gamma plus phi divided by 2 gamma. Let's now substitute it into the A tilde. We obtain obtain that 1/2 gamma here, gamma minus phi e gamma z plus gamma plus phi minus phi gamma z. Also here I z equal 1/2 gamma this is nothing else than cosine gamma z minus 2 phi I sine gamma z. And gamma z minus gamma gamma z. Now let's find the b tilde. Nothing else that conjugated minus 2 gamma z plus 1/2 gamma minus phi. And this is also easy to transform to sine function. So it's just 2I sine gamma z and the exponent. Now let's just calculate the absolute values. That's quite easy. It's just a cosine squared gamma z plus phi squared over gamma squared sine squared gamma z and b tilde squared and nothing else, just sine squared gamma gamma z, and sum up this expressions. B tilde, what we obtain cosine gamma z plus phi squared plus kappa squared divided by gamma squared sine squared gamma z. And we also remember that gamma, this is nothing else that phi squared plus kappa squared. So in the end, it is equal to 1. So what does it mean? It means that energy is conserved in our system. Actually, it is quite obvious because our system that we solved here, it is Hermitian one, Hermitian system. So already at the beginning, we could say that energy will be conserved in such system, but we just proved it. And let's try to plot these solutions. How? how they look like. Here, just 1 squared. We have some maximum at 1. And we have some value here because of our kappa. And it looks like something like this. Oops, I'm sorry. And if we will try to plot the b tilde squared, it will be something like this. So the energy flows from one mode to another. In this case, people say that gamma is just the crosstalk distance, and L just the 1 over gamma, and this, yes, it is just the crosstalk distance. It quantify actually the coupling of 2 different waveguides. So you can easily analyze the coupling strength that depends on the distance between the waveguides or resonators. So yes, actually today we just considered some basics of coupled mode theory. We considered arbitrary waveguides, but also it is applicable to arbitrary shaped waveguides, resonators, and resonators plus waveguides. So this is just the basics of the coupled mode theory. If you want to calculate some systems, the coupling between the waveguides, some ring resonators, for example, well, basically it is possible to do it with coupled mode theory. Yes. So that's all for me. From me for today. If you have any questions, ask. Well, if no more questions, we will stop here.
Excuse me, will we have another lecture or it was the last one?
Давайте я по-русски объясню. Смотрите, на следующей лекции, скорее всего, Илья разберет с вами какие-то задачи из домашек. Мы решили то, что с какими-то задачами были проблемы, поэтому их нужно будет разобрать. Поэтому, скорее всего, на следующей неделе будет защита, точнее, разбор домашек, а на последней лекции мы проведем midterm, защиту самих домашек.
То есть
Да.
то же самое, что было в середине семестра фактически, да?
Да. Ну, мы вам в начале курса обещали то, что в конце семестра тоже можно будет как-то исправить домашние работы, поэтому вот сделаем это на последней неделе. Да, вот здесь я хочу сказать то, что пара будет не во вторник, будет в среду в 11:40. Аудиторию я пока не знаю. Я попросил Дашу Замотину официально это передвинуть. Она куда-то поставила заявку.
А пара midterm, которая будет?
Да. она будет очно уже, поэтому да. В среду 25 числа.
А кто приедет точно?
А что, никто не приедет точно?
В смысле, из преподавателей?
А все будут точно.
Ого, хорошо.
Вот, да, мы все наконец-то возвращаемся.
Тут
Вот.
еще вопрос в чате один есть. Будут ли домашние работы?
Домашних работ, скорее всего, не будет больше. Ну, либо там будет какая-нибудь маленькая, супер маленькая, с одной задачкой, если будет. Но, скорее всего, уже нет.
А вот в теории, допустим, если исправлять по домашке нечего, то получается в среду можно не приходить?
Если нечего исправлять или не хотите ничего исправлять, то, конечно, можно не приходить, да.
Понятно. Ну, вообще схема остается та же самая, получается, да? Вот мы приходим там в среду с переделанными работами, которые хотим и можем показать, садимся к преподавателю и просто защищаем ее, да?
Да, все ровно так, как было на мидтерме, как мы договаривались.
А на экзамене же можно будет пользоваться конспектами?
На экзамене можно будет пользоваться конспектом при подготовке.
Понятно. То есть можно взять с собой, грубо говоря, свои конспекты, сесть, там все, что надо, воспользоваться, и когда сидишь к преподавателю, уже без всего, кроме того, что он написал при подготовке.
Да, конечно, конечно. И еще вопросы какие-то? Ну, если больше нет вопросов, то тогда всем спасибо и всем пока.
До свидания.